The efficiency of air conditioners is often rated by the seasonal energy efficiency ratio, which is defined by the Air Conditioning, Heating, and Refrigeration Institute in its 2008 standard AHRI 210/240, performance rating of unitary air conditioning and air source heat pump equipment. A similar standard is the European Seasonal Energy Efficiency Ratio. The Seer rating of a unit is the cooling output during a typical cooling season divided by the total electric energy input during the same period. The higher the unit Seer rating, the more energy efficient it is. In the US, the Seer is the ratio of cooling in British thermal unit to the energy consumed in watt-hours. The coefficient of performance, a more universal dimensionless measure of efficiency, is discussed in the following section. For example, consider a 5,000 British thermal unit per hour air conditioning unit, with a Seer of 10 a British thermal unit YH, operating for a total of 1,000 hours during an annual cooling season. The annual total cooling output would be 5,000 British thermal units per hour, 8 hours day, 125 days year equals 5 million British thermal units year, with a Seer of 10 British thermal units YH. The annual electrical energy usage would be about 5 million British thermal units year/10 British thermal units YH equals 500,000 YH year. The average power usage may also be calculated more simply by average power equals 5,000/10 equals 500 W. If your electricity cost is 20 cents per kWh, then your cost per operating hour is 0.5 kilowatts. 20 cents per kWh equals 10 cents per hour. Relationship of Seer to EER and COP. The energy efficiency ratio of a particular cooling device is the ratio of output cooling energy to input electrical energy at a given operating point. EER is generally calculated using a 95 AA degree Fahrenheit outside temp and an inside temp of 80 AA degree Fahrenheit and 50% relative humidity. The EER is a more realistic measurement of energy efficiency in warmer climates due to the high demand and higher cost of peak hour electricity. The EER is related to the coefficient of performance commonly used in thermodynamics, with the primary difference being that the COP of a cooling device is unitless, because the numerator and denominator are expressed in the same units. The EER uses mixed units, so it is obtained by multiplying the COP by the conversion factor from British thermal unit per hour to watts. EER equals 3.41214 COP. The seasonal energy efficiency ratio is also the COP expressed in British thermal unit YHR, but instead of being evaluated at a single operating condition, it represents the expected overall performance for a typical year's weather in a given location. The Seer is thus calculated with the same indoor temperature, but over a range of outside temperatures from 65 AA degree Fahrenheit to 104 AA degree Fahrenheit, with a certain specified percentage of time in each of 8 bins spanning 5 AA degree Fahrenheit. There is no allowance for different climates in this rating, which is intended to give an indication of how the EER is affected by a range of outside temperatures over the course of a cooling season. Typical EER for residential central cooling units equals 0.875 A. Seer is a higher value than EER for the same equipment. A more detailed method for converting Seer to EER uses this formula: EER equals minus 0.02 A, Seer squared plus 1.12 A. Seer. Note that this method is used for benchmark modeling only and is not appropriate for all climate conditions. A Seer of 13 is approximately equivalent to an EER of 11, and a COP of 3.2, which means that 3.2 units of heat are removed from indoors per unit of energy used to run the air conditioner. Theoretical maximum: the Seer and EER of an air conditioner are limited by the laws of thermodynamics. The refrigeration process with the maximum possible efficiency is the Carnot cycle. The COP of an air conditioner using the Carnot cycle is: where is the indoor temperature and is the outdoor temperature? Both temperatures must be measured using a thermodynamic temperature scale based at absolute zero such as Kelvin or Rankine. The EER is calculated by multiplying the COP by 3.412 British thermal units YH as described above. Assuming an outdoor temperature of 95 AA degree Fahrenheit and an indoor temperature of 80 AA degree Fahrenheit, The above equation gives a COP of 36, or an ER of 120. This is about 10 times more efficient than a typical home air conditioner available today. The maximum ER decreases as the difference between the inside and outside air temperature increases, and vice versa. In a desert climate where the outdoor temperature is 120 degree Fahrenheit, the maximum COP drops to 13, or an ER of 46. The maximum Seer can be calculated by averaging the maximum ER over the range of expected temperatures for the season. U.S. government Seer standards, Seer rating more accurately reflects overall system efficiency on a seasonal basis, and ER reflects the Systema Euro unregistered trademark S energy efficiency at one specific operating condition. Both ratings are useful when choosing products, but the same rating must be used for comparisons. As of January 2006, all residential air conditioners sold in the United States must have a Seer of at least 13. Energy Star qualified central air conditioners must have a Seer of at least 14. Today, it is rare to see systems rated below Seer 9 in the United States because aging, existing units are being replaced with new, higher efficiency units. The United States now requires that residential systems manufactured after 2005 have a minimum Seer rating of 13, although window units are exempt from this law, so their Seers are still around 10. Substantial energy savings can be obtained from more efficient systems. For example, by upgrading from Seer 9 to Seer 13, the power consumption is reduced by 30%. It is claimed that this can result in an energy savings valued at up to $300 per year depending on the usage rate and the cost of electricity. With existing units that are still functional and well maintained, when the time value of money is considered, retaining existing units rather than proactively replacing them may be the most cost-effective. However, the efficiency of air conditioners can degrade significantly over time. Therefore, maintenance should be performed regularly to keep their efficiencies as high as possible. But when either replacing equipment, or specifying new installations, a variety of Seers are available. For most applications, the minimum or near minimum Seer units are most cost-effective, but the longer the cooling seasons, the higher the electricity costs, and the longer the purchasers will own the systems, the more that incrementally higher Seer units are justified. Residential split-system AC units of Seer 20 or more are now available, but at substantial cost premiums over the standard Seer 13 units. The higher Seer units typically have larger coils and multiple compressors. The cost reflects the additional complexity. U.S. government Seer requirement changes for 2015. In 2011, the U.S. Department of Energy revised energy conservation rules to impose elevated minimum standards and regional standards for residential HVAC systems. The regional approach recognizes the differences in cost optimization resulting from regional climate differences. For example, there is little cost-benefit to having a very high Seer air conditioning unit in Maine, a state in the northeast U.S. Starting January 1, 2015, split-system central air conditioners installed in the southeastern region of the United States of America must be at least 14 Seer. The southeastern region includes the following states: Alabama, Arkansas, Delaware, Florida, Georgia, Hawaii, Kentucky, Louisiana, Maryland, Mississippi, North Carolina, Oklahoma, South Carolina, Tennessee, Texas, and Virginia. Similarly, split-system central air conditioners installed in the southwestern region must be a minimum 14 Seer and 12.2 ER beginning on January 1, 2015. The southwestern region consists of the states of Arizona, California, Nevada, and New Mexico. Split-system central air conditioners installed in all other states outside of the southeastern and southwestern regions must continue to be a minimum of 13 Seer, which is the current national requirement. These new requirements are being challenged by industry trade groups. Calculating the annual cost of electric energy for an air conditioner, electric power is usually measured in kilowatts. Electric energy is usually measured in kilowatt-hours. For example, if an electric load that draws 1.5 kilowatt of electric power is operated for 8 hours, it uses 12 kilowatt-hours of electric energy. In the United States, a residential electric customer is charged based on the amount of electric energy he or she uses. On the customer bill, the electric utility states the amount of electric energy, in kilowatt-hours, that the customer used since the last bill, and the cost of the energy per kilowatt-hour. Air conditioner sizes are often given as tons of cooling, where 1 ton of cooling equals 12,000 a British thermal unit per hour. 1 ton of cooling equals the amount of power that needs to be applied continuously, over a 24-hour period, to melt 1 ton of ice. The annual cost of electric energy consumed by a 72,000 a British thermal unit per hour air conditioning unit, operating for 1,000 hours per year, with a Seer rating of 10, and an electric energy cost of 12 cents per kilowatt-hour is, unit size, British thermal unit per hour, hours per year, HA, energy cost, dollar per kilowatt-hour is Seer, British thermal unit per watt-hour 1,000 watts per kilowatt, example 1, 72,000 British thermal units per hour, AA equals $860, example 2. A residence near Chicago has an air conditioner with a cooling capacity of 4 tons and an Seer rating of 10. The unit is operated 120 days each year for 8 hours per day, and the electric energy cost is 10 cents per kilowatt-hour. What is the annual cost of the electric energy required to operate the air conditioner? First, we convert tons of cooling to British thermal unit per hour. 4 tons, equals 48,000 British thermal units per hour. The annual cost of the electric energy is 48,000 British thermal units per hour. AA equals $460. Maximum Seer ratings. Today there are many split air conditioner units available with Seer ratings up to 27.2. During the 2014 AHR Expo, Mitsubishi unveiled a new mini-split ductless AC unit with a Seer rating of 30.5. Traditional AC systems with ducts have maximum Seer ratings slightly below these levels. Also, practically, central systems will have an achieved energy efficiency ratio 10 to 20% lower than the nameplate rating due to the duct-related losses. Additionally, there are ground-source residential AC units with Seer ratings up to 75. However, ground-source heat pump effective efficiency is reliant on the temperature of the ground or water source used. Hot climates have a much higher ground or surface water temperature than in cold climates and therefore will not be able to achieve such efficiencies. Moreover, the ARI ratings scheme for ground source heat pumps allows them to largely ignore required pump power in their ratings, making the achievable Seer values often practically lower than the highest efficiency air source equipment particularly for air cooling. There are a variety of technologies that will allow Seer and EER ratings to increase further in the near future. Some of these technologies include rotary compressors, inverters, DC brushless motors, variable speed drives and integrated systems. Heat pumps. A refrigeration cycle can be operated as a heat pump to move heat from outdoors into a warmer house. When operated in heating mode, a heat pump is typically more efficient than a resistance heater. This is because a space heater can convert only the input's electrical energy directly to output heat energy, while a heat pump also transfers heat from outdoors. In heating mode, the coefficient of performance is the ratio of heat provided to the energy used by the unit. An ideal resistance heater converting 100% of its input electricity to output heat would have COP equals 1, equivalent to a 3.4 ER. However, when a heat pump operates near its most inefficient outside temperature, typically 0 degree Fahrenheit, the heat pump's performance may be comparable to a resistance heater. Lower temperatures may cause a heat pump to operate below the efficiency of a resistance heater, so conventional heat pumps often include heater coils or auxiliary heating from LP or natural gas to prevent low efficiency operation of the refrigeration cycle. Cold climate heat pumps are designed to optimize efficiency below 0 degree Fahrenheit. In the case of cold climates, water or ground source heat pumps are the most efficient solution. They use the relatively constant temperature of groundwater or of water in a large buried loop to moderate the temperature differences in summer and winter and improve performance year-round. The heat pump cycle is reversed in the summer to act as an air conditioner. See also, air conditioner, air conditioning, annual fuel utilization efficiency, coefficient of performance, Energy Star, heat pump, HSPF, HVAC, thermal efficiency. References. External links, a new measure for the energy efficiency of heating and cooling devices, information from DACIN on seasonal efficiency, climate impacts on heating's seasonal performance factor and seasonal energy efficiency ratio for air source heat pumps.